What is calculus? It's a commonly asked question. Depending on your pathway in life, you may never have to take calculus. But even people who do take calculus, a lot of times they get drowned in the details and they don't really see the big picture. And so the purpose of this video is to shine light on to what calculus is all about and give you a good foundation moving forward. So, the easy answer, it's a branch of mathematics, right? And so it involves derivatives and integrals of functions, including curves, which is great. And that just has to do with slope and area, which I'm sure you've heard of before. And this happened right around the scientific revolution time, where modern science was coming about. And so we were in the 1600s, and we had Newton and Leibniz conceiving these ideas independently of each other. And Isaac Newton was an English mathematician, and you had Leibniz as a German philosopher. And what they did is they incorporated this idea of continuous change and infinitesimal differences, so infinitely small differences, and this also idea of limits, and so you're approaching values. And so applications for this is all over the place. Obviously mathematics itself, but science like physics, and also economics, engineering, medicine, etc. We'll get more into that later. So the first thing we really need to talk about is functions. And so a function is just something that explains how a varying quantity depends on another one. And you have an input and an output. And so imagine that you have your input here and you have your output, you have your domain and your codomain, and then you have some values that you're inputting, and we're going to map them over, and the ones that they hit are going to be the range. You might have some left out. But the idea is that you have this variable, and a variable is something that can change, and it has a value at a particular point. I like to think about this like the weather. The weather can be a variable. But in math, a lot of times we use the dummy variables x and y, right? And a constant is something that does not change. And so a common example of a function that you're probably familiar with is the line y equals mx plus b. And so that has x values called the domain and y values called the range. And so you have that input and output. And so in this equation, that y is the variable, and that's your output, and the x is a variable, and that's your input, and your m is your slope, and that's telling you the steepness of the line, and then the b is the constant y-intercept, and so that's where it crosses the y-axis. And this function only depends on the value of x, and so many times what we'll do is instead of writing y, we'll write f of x. So this is a function depending on that variable x, that input x. So if you look at how you would go about graphing this, well, if we use Cartesian coordinates, there's other coordinate systems too, like polar. But if we use Cartesian, the way that we do it is we have a fixed reference point, like an origin here at the point 0, 0. And we have these coordinates that measure perpendicular distances. So you have your y-axis, which is perpendicular to your x-axis, 90 degrees. And then you are measuring out a certain distance on that x-axis and then up on the y-axis to get to the coordinate that's on your function. And so if you had a x value of a, this would be your function evaluated at that a. And then this would be an x value of b, and then the function evaluated at b. This kind of brings us to the intermediate value theorem. And so pretty much what this says is if you have a function that's continuous, pretty much it is something that as you draw it, you don't have to pick up your pencil. It's an unbroken function. And you have this number n. Bottom line is if this n is somewhere between this f of a and f of b, then there's got to be some sort of a c value for your input that's going to result in a output, the function evaluated at c, where it's going to be equal to that n. Basically what it's saying is that it's going to at some point cross this line, so the function crosses that line. So that's pretty much what a continuous line is all about, a continuous function is all about. So we keep going here, We got the vertical line test for a function. And so if you were to do the vertical line test, what it's telling you is if you have a function or not. And so if you have this vertical line and you have more than one dot here, so more than one value, then there's an issue. And so that means that for a given x, you have multiple outputs. That just is not looking good. And then you can also look down here. This is looking pretty good, all right? So for this vertical line, there is only one. All right, now we can look at the horizontal line test, and that's pretty much going to tell you if it's 1 to 1. And so if we look here, it looks like for this given y value, it has two different x that could get you to that. And so that's kind of an issue. And then here, for this given y value, it's just got 1. So that's nice. So it's 1 to 1. And so if you want to get a little bit more detailed into what this 1 to 1 is all about, it pretty much means that for every x, you are mapping it 1 to 1 to your y. And notice how this is not onto in this case, because you can kind of see the issue, right? We have 3 elements in our x here, and then we have 4. So there's really no easy way to match that up nicely. And then down here, this is onto, but it's not 1 to 1. So you see how it's not a nice 1 to 1, but it is onto, and you can see how there's still kind of an issue here, where you have 4 things over here and only 3 things over here. But if you combine these nicely, so 1 to 1 is something called injective, and onto is surjective. And then if you combine them together, you get a nice perfect mapping, and then it's called bijective. All right. So now we get into the y-axis and the x-axis again, and we're going to graph this simple function. And so we have this function y equals mx plus b, and we have an initial x coordinate and a final x coordinate, and then we have a initial y coordinate and a final y coordinate. All right, and so we got these points here. Now we can look at the change in the x and the change in the y, and so we pretty much say that how much is this line running and how much is it rising. And so when we take the rise divided by the run, the change in the y divided by the change in the x, the final y coordinate minus the initial y coordinate, the final x coordinate minus the initial x coordinate, when we do that, we get the slope. And so if we wanted to be more specific, what we could do is we could actually come up with a line. And so we'll just do a very simple line. So this is just 1, 1, 2, 2. So whatever you're putting in is what you're getting out. That's a pretty simple function. So what does that look like? Well, we're going to take our generic form for a line and we're going to adapt it. And so in this case, we have 1 is our run and 1 is our rise. And so we have 2 minus 1 over 2 minus 1. So pretty much 1 over 1 is 1. So our slope is just 1. And we have 1 that we plug in there. And it crosses the y-axis at 0. And so our b is just 0. And so we could just rewrite this function now as y equals x. Or, remember, we could write it as f of x equals x. And so this is the function we're going to be dealing with. And I wanted to keep it simple on purpose. All right. So the next thing is limits. The limit of a function is the limit value L right here that the function f of x gets closer to as x approaches this value a. And it's written as the limit of this function as x approaches a is equal to that limit value. It's important to realize that this limit is not the same thing, this limit value is not the same thing as the actual value of the function at a. And so anytime you deal with this limit problem, it's not really asking for f of a, it's asking for what happens near as you approach a. And so we don't really care about what it actually is. All right, so limits are similar to asymptotes. And so you've probably heard of this before, where you're approaching zero distance between the asymptote and the function. And then you also deal with approaching when you are talking about end behavior, and so a function and how it behaves as it approaches positive or negative infinity. And the same thing can kind of happen with limits, where we can look at the limit value as we approach positive or negative infinity. And then we got to get into what a hole is. So a hole exists anytime you have an input value that causes the numerator and the denominator, the top and the bottom, to be zero. And it just creates a problem there. But it's not as big of a problem as we might think in this case, because remember, we don't actually care about the value at that hole. And so just because the function doesn't really exist there, it's not really the end of the world in this case. But remember, we got to be able to approach it from the left and the right. And so one thing we can do with a one-sided limit is come in from the left, the negative direction, and see what we're approaching. And then we're going to come in from the positive direction and see what we're approaching. And in order for that limit to exist, it has to approach the same value from the left and the right. All right, so let's look at what we have. We have our simple function here. And one thing we could do is create this problem. And one easy way to do that is multiply and divide by the same thing. So you're not really changing the function all that much. But what you are doing is creating this issue at this value of 1.5. And so you plug in 1.5 for x, and you can see what happens. And you end up getting 0 on the top and bottom. And so now we have a issue at that point. And so we just kind of created a hole there. All right, well, let's look at the limit. Well, let's first look at it from the left. And so we'll get closer and closer and closer from the left. And then we'll look at it from the right side, and we'll get closer and closer and closer from the right. And notice how they're both approaching that 1.5 as you get closer from either direction. And so we know that the overall limit then is just going to be 1.5. No big deal. So some other examples would be this function right here. And so in this case, we can try just to plug in the value here. So as x approaches 0, just try to plug it in and see what happens. And we do that. It turns out we get 3. And so as x approaches 0, that limit value is going to 3, which is awesome. All right, so next example, we might run into an issue here when we try to plug in 1/2. And so we plug in 1/2 and we get 4 over 2 is 2 minus 2. Okay, that's 0 on the top. It's not crazy bad. But then we look at the bottom and we get the square here. So we got 1/4 times 6. That's 6/4 plus, well, we can rewrite that 1/2 as 2/4. And so 6/4 plus 2/4 is 8/4, which is 2. 2 minus 2 is 0. Uh-oh. That's a 0 over 0. So what can we do? Well, let's not call it quits. Let's see if we can factor it. So if we can factor this, well, we can factor a 2 out, and then we can factor this bottom as well. And so we can kind of check to make sure that we can get it back. So 2x times 3x is going to be that 6x squared. And then the 2x times the 2 is going to be 4x. And then the 3x times the negative 1 is going to be the negative 3x. And so 4x minus 3x is just x. And then I check the last one is negative 1 times 2. And then I get back to that negative 2. So it looks like I'm good here. Great news. We can cancel out the top and the bottom here. Like this 2x minus 1 exists on the top and bottom. So that's gone now. And then we can plug in the 1/2 and we can see what happens. See if we fixed our issue. And so now we have 3/2, and then 2 can be rewritten as 4/2. So we have 3/2 plus 4/2, which is 7/2. And then if we divide by a fraction, that's the same as multiplying by the reciprocal. 2 times 2 is 4. Okay, 4/7. That's awesome. And so we could actually use L'Hopital's rule to do that as well, but we haven't learned about a derivative yet, so let's leave that for a different day. Alrighty, so next example. Okay, limit as x approaches infinity of the square root of x minus x. Well, we plug that infinity in and we really get a big number minus a big number, and so that's kind of an issue, right? That doesn't really tell us much. So let's try to factor it. Well, when we do that, well, we can factor out a square root of x, and so when we distribute it back in, we get that square root of x minus x, because the square root of x times the square root of x is just x. And so this looks okay. Well, does that help me? Well, I can kind of see how it's going to help me. Well, this is the square root of infinity. This is going to be a big number, and then 1 minus a big number is going to be a negative big number. And so a big number times a negative big number is just going to be a negative big number. So as x approaches infinity, the function is approaching negative infinity. All right. So the last one is this one. So x approaches 0. Let's try to plug it in. And you'll see very quickly that we run into an issue. We have a divide by 0 problem. And so let's see if we can look at what's happening from both sides. Well, if we approach 0 from the negative direction, so we have negative numbers that are approaching 0 on the number line, well, I can kind of just focus on the problem area, which is the denominator. All right, so on the top, I'm just going to have 1. Let's focus on where the problem was. Well, I'm really just going to have the 0 multiplied by that negative 1. And so I'm specifically interested in the 0 coming from the negative direction. And the 0 coming from the negative direction is going to give me negative values. And so that's going to be multiplied by another negative. So now it's pretty much the same as approaching that 0 from the positive direction, because I have the two negatives multiplied by each other. And so 1 divided by a small positive number is going to give you a big positive number. So you get positive infinity coming from the left. And now coming from the right, we get the opposite result. And so we're actually approaching different things, and we have some asymptote stuff going on. And so the limit does not exist because you're not approaching the same thing, right, from opposite directions. So we just can't really say much. All right. So the next thing we got to talk about is derivatives. A derivative is a way to show instantaneous rate of change, which is pretty much your slope, and that's symbolized as some small change in y over some small change in x, dy over dx, or y prime. Now you can also replace that y with your f of x, and that's assuming that your function's varying with x. So that's how you symbolize a derivative. But let's talk about how it's defined. And so you can use this idea of a limit. And so this small change in y over the small change in x can be defined with a limit. And we got to go over here to understand it though. So we have some x value, and we have at some later point some change that we had happen. And so that change in x is represented here. And we can also plug in what is the function at x and what is the function at that x plus the change, right? And so what happens is you have this change in y and this change in x. And as this delta x approaches 0, so as this gets closer, this is going to be getting closer, right? So you're pretty much approaching a single point. You're approaching a very small change. Now we can start to use dy and dx, and that's what this is telling us, all right? And so really what we're talking about is that the derivative is the slope of the tangent line at a point on the graph. And so if we have a curve, this was kind of boring because the slope is like the same the whole time, but if we have a curve, it makes a little more sense because the slope is actually changing of the tangent line, and the tangent line is just a line that touches the graph barely, just once. And then the secant line sometimes you talk about as well, and that's touching the line in at least 2 distinct points. But the bottom line is the slope of that tangent line is really what a derivative is looking at. And so we can look at the mean value theorem for derivatives. We can pretty much say that if a function is continuous on this closed interval from a to b, and we also know that this first derivative exists, then we have some c value that we could use. And if we were to take the derivative of the function, if we were to look at the slope at that value, c, at some point, there's got to be a point where it's equal to the slope of this line right here. So pretty much f of b minus f of a, and then b minus a. So your change in y over your change in x. And so that pretty much has to do with the average. There's got to be at some point the slope's got to match up. It's not that big of a deal. And then also over here, Rolle's theorem is very similar to that. So if you move this point up here and we have f of a is equal to f of b, then in this case you're going to have pretty much a horizontal line at some point. And so at some point the derivative is going to equal 0. And that just pretty much represents a 0 slope, a horizontal line. All right, so the next thing we're going to talk about is the idea of, is a function always going to be differentiable? Well, not necessarily. So it only is differentiable at a point A if the derivative at that point exists, all right? But that doesn't exist at, for example, a sharp point. So if you look at this function, you have a very sharp point there. We don't like that because we have a positive slope, and all of a sudden we have just this quick, ridiculous change to a negative slope, and so that's not good. And we could also have a vertical tangent line, which is right here, and so that's pretty much infinity here. So imagine the slope is like straight up and down, and so that's kind of an issue too. All right, so the next thing we could look at is what we can do with this first derivative. And remember, it's telling us about the slope. We can actually find information on the slope and critical points. Well, what does that mean? Well, bottom line is if we look at where the slope is equal to 0 or does not exist, so we have, do you see how these lines are horizontal, these tangent lines? So the slopes are going to be 0 here. Now we're going to have these two critical points at these two spots right here. And anytime you're switching from a positive to a negative slope, up to down, we're going to have some sort of maximum point. And then if you're going from a negative slope to a positive slope, you're going to have a minimum point. And so this is really awesome. We can do the first derivative test to find maximum and minimum points. And we can also use the second derivative test. And this tells us about concavity. And so notice how there's a double prime here. And so when we look specifically at this critical point that we were looking at before, well, if we have a minimum, it's going to be concave up. And so I can remember this like smiling is up, like you're happy, you're positive. And then frown is down, right? And so that's negative. And so if we're concave up, that must mean that we have a minimum. And if we're concave down, then that must mean that we have a maximum at those points. But you don't necessarily always have to be evaluating the first and second derivative at those, critical points. You can do it at whatever point you want. So you want to test some areas. And so another cool thing is if you have a switching concavity, so this is a negative concavity to a positive concavity, at some point you had to have that second derivative equal to 0. At some point you went from a negative to a positive. And so you had to pass by 0, and then you have an inflection point, which is pretty awesome. And so this brings us to the extreme value theorem, which is pretty simple. It pretty much just says if a function is continuous on a to b, all right, then there's a guaranteed absolute minimum and maximum on the interval somewhere. There's got to be some maximum and minimum points. Now there can be local minimum and maximums and absolute minimum and maximums, but bottom line is that theorem holds true. So our example, though, back to our simple example, is a straight line and it's a first degree polynomial, which means the highest number is 1 in the power. So its highest power is 1. And so we can look at our line here, y equals ax plus b, where a represents the slope. Or if you had a second degree here, we would have y equals ax squared plus bx plus c. Or if we had the highest power, be 3, and so on. Bottom line is, anytime we have something like this, where we have a power, we can use a derivative rule. Now, there's a lot of derivative rules, but this is the main one that we're going to learn. And so, bottom line is, we can take the derivative of this function by just taking whatever the power was, subtracting 1 from it. And we also have to multiply the power down front. So you can think about it like just multiply down front and then subtract 1 from the power. All right. So we look at our function here. We just have a simple function. Now, we have a slope of 1, as we've discussed. So we look at the derivative, and we say, okay, well, my function is x to the first power. Well, let me do that rule I just learned. So x to the first power. All right, what would I have to do? I got to multiply down front, and then I got to subtract 1 from the power. So 1 minus 1 is 0. Okay, so 1x to the 0. X to the 0 is just 1. Okay, well, that tells me my slope is just 1. And it also tells me that it doesn't really depend on x at all. Like, it's a constant slope everywhere, which makes sense because it's a line. It's a straight line. It just has a constant slope. So that's kind of boring. But that's pretty awesome that it agrees with what I already knew, right? All right, next one. Another example, right? And so what we can do is look at a constant. What happens when you take the derivative of a constant like 1 or 5 or 500? Well, you can imagine that there is x to the 0 there. And that 0 comes down with our rule, right, and multiplies. And we can pretty much stop there because, we're going to get 0. And so we just learned that the derivative of a constant is just 0, which kind of makes sense because a constant is going to be a horizontal line, and the slope of a horizontal line is going to be 0. All right, next, x squared. So now we get a little bit more complicated here. Well, I can multiply that 2 down, and I can subtract 1 from the power. I get 2x to the first, which is just 2x. And so now I get an answer that actually the slope is a little bit dependent on which x value I'm at. Okay, so now the third one, I'm going to add a 3 here, and so I can do the same thing. I multiply the 2 down, I get a 6, I subtract 1 from the power, and I get 6x. And for the last one, we can try a negative power. Well, a negative power is okay, we can do that. So we're going to subtract 1, so negative 2 minus 1 is going to be a negative 3, but I had to also multiply that negative 2 down to give me negative 6. And so now I have negative 6x to the negative third, but x to the negative third can also be written as a positive if I throw it down into the denominator. So it's negative 6 over x cubed. And so those are some other examples for you. The next thing we got to talk about is the integral. An integral or antiderivative is pretty much just looking at the area. And so we look down here, we got our point x and x plus some sort of a change that happened, and then we can look at the y values at those locations. And really what we want to focus on is this green rectangle, and we know that we can get the area of that by just multiplying the two sides. And so one of the sides is pretty much represented by f of x, and then the other side is pretty much represented by this change in x. And as this change in x gets very, very small, it pretty much becomes dx, and it pretty much perfectly then matches that area under the curve. And so the way I like to think about it is that the area is equal to this function of x here, f of x, times dx. And so that literally is an area multiplication right there. And then I like to think about this as a sum symbol, and so you're adding up all of them. And so that's the basic idea of what an integral is all about, is trying to find the area under a function. And that function is varying with x. All right, and so we can also have a definite integral, and that's one that has bounds. And so we have a and b, and we're pretty much confining our area to a certain space. And we have bounds then, a and b. We can also look at the mean value theorem for integrals. That's pretty much saying that if a function is continuous on a to b, and you also have that first derivative existing, then there's got to be some value c here where it corresponds to this f of c, and it pretty much is drawing out this rectangle for us, and that area of that rectangle has got to be equal to the area under the curve. At some point that's got to happen. And so you can see how the missing area here is pretty much made up for by the area here. And so at some point along that curve, it's got to happen. All right, now a Riemann sum is an approximation which adds up all these little rectangles, And then you can also have the trapezoidal rule, and it adds up trapezoids, but those are just approximations. And so we also have something called an indefinite integral, and then you don't have any bounds at all, and so it's really hard to like actually evaluate, so we just always have this constant of integration, so we don't really know where we're integrating. All right, so our example, remember, is a straight line, and our straight line can follow this power rule, and we had a power rule for derivatives. There's also a power rule for integrals. Now there's a lot of other rules as well for different functions, but we're just dealing with this simple rule, and the same ideas apply with the other rules. So we got our function here, and it's just y equals x. We can take the integral, which we're pretty much adding up all of the area with that dx and that f of x. We're adding up all the area under that function, and we end up doing our rule here. In this case, it's pretty much the opposite, and so it says that when you have x to the power of n, you have to add 1 to the power and then divide by it. And you got this plus c as well, the constant of integration. So I'm going to start off with my 1 power. I'm going to add 1 to it and then divide by it, and so I get x squared over 2 with this c here. So very similar to the power rule for a derivative. Another example is the integral of a constant. And so when you take the integral of something like 1, imagine that you have the x to the 0 there. It's an invisible x to the 0 because x to the 0 or anything to the 0 is 1. And so you can throw it there, no big deal. We can use the power rule on it. And so 0 plus 1 is going to be 1, and then divided by 0 plus 1, and so you end up just getting the x back. And so that's pretty cool that when we take the integral of a constant, we get back the x. The next one we're going to look at is the integral of x squared, and we can add 1 to the power and divide by it, and we get 2 plus 1 is 3 over 2 plus 1 is 3, and so x cubed over 3, and we got that constant of integration again. The next one, we'll put the 3x squared in there. This time we're going to do the 2 plus 1, but we're also going to divide by it, and that 3 is actually going to cancel out nicely for us, and we just get x cubed. The last one, we can take the integral of 3x to the negative 2 power, and we still add 1 and divide by it, and we end up with a negative 1 on the bottom. We can take that negative, put it out front. We end up with x to the negative 1 power, and then we can move that down into the denominator, and so we end up with negative 3 over x. Alright, so the next thing we got to talk about is the fundamental theorem of calculus. For this, we're going to have a capital F of x representing the integral or antiderivative of your function f of x on this closed interval from a to b. And so the first part deals with the derivative of an antiderivative, which is pretty much just undoing itself, and you're going to get back the original function. And so the practical part of this theorem here is that this capital F, which represents the integral or antiderivative, once you take the derivative of it by this prime symbol, you're going to be left back with what you started with. So the second part of the theorem deals with the relationship between antiderivatives and definite integrals. Here, the practical part is talking about this definite integral from a to b, and so you're integrating this function from a to b. You're trying to find the area from a to b under the function here. And what this tells us that we can do is it tells us that we can take the integral and then we can evaluate it at b, and then we can subtract it from the integral evaluated at a, and we end up with the answer. So that's awesome. It gives us a way to actually evaluate our definite integrals. And so what we can do is go back to our simple function, and we can look at our rule from before, and we can look at this triangle shape here, the area under the curve here, and this is from 0 to 1 in this case, and we're going to try to find the area under our function from 0 to 1. So we got to take the integral of our function, which we did before. We just add 1 to the power, so it's x squared, and then divide by it. And then we evaluate it, though, from 0 to 1. What does that mean? Well, let's look up in what we have to do here. Well, we took the integral, and now we have to plug in the b. So we'll plug in 1, that's our b value, and then subtract the integral evaluated at the lower bound here, the 0. And so the nice thing is that's just gone. So it's 1 squared, which is 1 over 2. So that's just 1/2. Also, we could look at the geometry. And this area is just the area of a triangle, right? And we hopefully remember that the area of a triangle is 1/2 base times height. So maybe this will kind of convince you what's going on here. So the base of this triangle is 1, the height is 1, and so we could do 1/2 base times height and we get the same thing. So the next thing we could do is look at the integral from 0 to 2, and we do the same exact thing, but this time we're plugging in 2 and 0, and we get 2 squared, which is 4, and then we get 4 over 2, which is 2. We look at the geometry, we got a 2 for the base, a 2 for the height, and so we end up with the same with our geometry formula. The other thing we could look at is a little bit more complicated. So now we're looking at the area from 1 to 2. So now we have to subtract off this area here. And so notice how we got our 2 squared over 2 just like before, but this time we actually have to plug in this 1 here. And so we're going to end up with 2 squared, which is 4 over 2, minus this is going to be 1 over 2, and so 4 over 2 minus 1 over 2 is 3 over 2. And then we can look at the geometry here, and we can pretty much just take the area of the bigger triangle minus the area of the smaller triangle, so 2 minus 1/2, and we end up with 3/2. So pretty awesome that that agrees. Let's look at some other examples. So we have this integral of a constant like we saw before. This time it's from 0 to 1, and so we pretty much just have x, and so we plug in and we got 1 minus 0, which is pretty much just 1. The next thing we could do, same as before, but this time we can evaluate it from 0 to 1. So we got x cubed over 3, and so we got to evaluate that. 1 cubed over 3 minus 0 cubed over 3, and we get 1/3. Next one we could do is 3x squared, but this time we're going to go from 1 to 2, and so we get our 3x cubed over 3, but we're going to plug in 2 and 1, and so 3 times 2 cubed over 3 minus 3 times 1 cubed over 3. We end up getting 8 minus 1, which is 7. Last one, from 1 to 2. We're going to take the integral of 3x to the negative 2. Remember, we did this before, and we got the negative 3 over x, and we're going to evaluate it from 1 to 2. And so we're going to have 2 plugged in down here and 1 plugged in down here, and we end up with an overall answer at the end of 3/2. So, pretty awesome. This really opens the door into a lot of applications. Remember that calculus is a branch of mathematics from Newton and Leibniz, and it involves derivatives, which has to do with the slope, and integrals, which has to do with the area, like we talked about. One thing to point out, though, is there's a lot more to learn, like multivariable calculus, partial derivatives, double and triple integrals, different coordinate systems, etc. There's also a lot more rules, like product rule, quotient rule, chain rule. There's a lot of other functions like trig functions, hyperbolic functions, log of x, and so really the main goal here is that we're trying to accomplish that derivative and integral for these different functions, and so we have different methods to go about doing that. So one of the key applications has to do with optimization. So you have calculus that can determine marginal revenues and costs, and it can maximize your profits. It can find rates of increase in profit from each increase in production. You can also have calculus for determining the amount of interest paid over the life of a loan. You can also have calculus to figure out the rate of blood pumped through the heart per unit time, and so really any rate that you can think of. And then also to analyze the motion of planets, right? And then more of a specific application that I use a lot is in physics. We have ideas such as impulse, which is change in momentum, which is the integral from the initial time to the final time of your force function. And you also have this idea of acceleration. And so you have an acceleration function, which is pretty much the derivative of your velocity. And you have your velocity function, which is the derivative of your position with time. And then you have your position function. And so we can kind of see that impulse here. And so we're really just, in order to get that impulse, we have a force per unit time. And then we look at the area under that curve to get your impulse. And then the other thing we can do is look at graphs like this with position, velocity, and acceleration and realize that, for example, a point like this that has a constant slope, well, that makes sense that the derivative then is going to be a flat line. We can also look at how this right here is a flat line, so that slope is 0, and down here it transfers to 0. Same thing here, the slope at the top here is 0. We're going to transfer that down to here, and that is 0. And so really what we just learned is that as we go down from position to acceleration, we're just taking the derivative, and then as we go back up, we can take the area under, and so we're taking the integral to get back. And so this is really useful with kinematics and analyzing motion. So I hope that that helps, and I hope that that shines some light onto calculus and why it's important and some of the basic ideas involved. See you next time.